Welcome to the 1955 Nobel Prize in Physics. I'm calling this one the Quantum Electrodynamics Prize because it involves a couple things in that field. So we'll get to that. This prize was divided between Willis Lamb and I'm going to get this name, pronounce it wrong, apologize for that, Polykarp Kusch. I think I have that close. Willis Lamb won for the discovery of some really cool stuff involving the fine structure of the hydrogen atom inside the hydrogen spectrum of the spectrum of the hydrogen atom. Professor Kusch won for precision measurements of the magnetic moment of the electron. Now, all that sounds like stuff that's been done before, right? And it is. But we're going to get to why this group was different than those that came before them. Okay. Now, all of these discoveries are actually enabled by newer technologies and lab equipment that we could get more out of than than scientists used to be able to get. So this work was kind of done in the 40s, late 1940s. They didn't win the prize until the 50s. So that's kind of why it occurred then, right? So before then, a lot of the work done on these same measurements was sort of in the 30s and the 20s. But now new lab equipment was available. So they went and redid a bunch of measurements, got more precise, and they learned new things. And it's not just about, hey, instead of, this accurate, we're now this accurate. There's a lot more to it. There's new things that popped out, new surprises that came about. So first, what is quantum electrodynamics before we get too far? Let's understand what we're talking about. Quantum electrodynamics is really how light interacts with matter. So how light bounces off a mirror, how light passes through a window, how light interacts with matter. That is really all we're talking about. It's a big fancy way of saying it, but you have to learn the language of physics. Now, it does something else. It was really the first theory that was in full agreement in between quantum mechanics and relativity. So what you've got now is this way of describing how light interacts with matter down at an atomic and below scale. So it does it at a scale that's not like, my desktop. It's not the size of the window. It's down at the individual atom or particle level. And that's what makes it a little bit different. And the discoveries that start coming out are really kind of interesting. Now, because those two things are in agreement, quantum and relativity, you may be asking, hey, so is this the theory of everything? Well, no, because it's only really involves light and matter. The theory of everything would have quantum and relativity in agreement in all kinds of places, and there are spots where you want to know more about just light, about more than just light and matter. So this is part of the way there, and even quantum electrodynamics does have some limitations to it, but it is really the first one where you started to see a much better agreement in between relativity and quantum mechanics, which is something that those two just are still kind of arguing with each other. So let's dig in a little bit and see what each of these two guys did individually to be deserving of the prize. First, let's dig into Willis Lamb. So when I talked about the 1922 Nobel Prize, we talked about Niels Bohr. And I said that he had this model of the hydrogen atom that won him the prize. And everybody said, well, it's great. This is perfect. It does everything. And I said, it's not exactly perfect. But I also said at that time that they didn't know it wasn't perfect until later. Now we're about to find out what's wrong with it. So from what was known then, it was great and until it wasn't. But when you have, let's talk about the fine structure of the hydrogen atom. So when you have an electron go from that excited state, it's up, it came out of its ground state, it got excited, it got pumped up to a couple of layers up, in which I explained in deep detail in the 1922 prize, which that video's on the playlist. And then it comes back down. What you get is some kind of an emission from that atom. You get some kind of a signature that you can then go measure and say, okay, well, that's hydrogen going from one state to another state, and it spits something out. I'm like, great, I understand what that is. Okay. Well, what Lamb did was he discovered very small anomalies in those signatures that just didn't fit the theory that was wrapped around at the time. And those shifts couldn't even be explained by these things called the Dirac equations, which Dirac was this theorist that came up with all kinds of ways of explaining how all this stuff worked. And it was pretty accurate, but this one didn't fit. The Lamb shift could not be explained by Dirac. And it thought, maybe it was caused by something called quantum vacuum fluctuations. Well, in fact, it is caused by something called quantum vacuum fluctuations. But what are quantum vacuum fluctuations? Big, fancy, huge set of words there. You're like, holy crap, that's scary. Well, what those things are, it's a temporary change in the amount of energy at a point in space. And it apparently is random according to theory. there's really not a big way to predict what it is. You can induce it to happen, you can cause it to happen, you can set the stage for it to happen, but you can't really decide when it happens. But again, this is another one of those problems I have with quantum mechanics, that it appears random. We say it's random. I suspect it's not. I can't prove that it's not, but to me, nature doesn't do random stuff. There's something causing it. We just don't know what it was. But this slight shift in that theory that came out of the Dirac world, the previous world, the Niels Bohr Dirac space, we say, okay, well, we don't understand what it is. This is new. Holy crap, what is it? Quantum black function, throw a big name on it, right? So the discovery of the Lamb shift actually led to a lot of theoretical work being done, and it took a bunch of people whose names are going to sound familiar to you to really kind of explain what was going on. He observed it. He said, here it is. I don't know what it is, but he published it. He put it out in the world, and it took years, and people like Julian Schwinger, Richard Feynman, Ernest Steckelberg, and Freeman Dyson to kind of come along and come up with a rational explanation for it, and they eventually did. They're very technically detailed, and I'm not going to talk about them in this video, but basically it boils down to they had to kind of go start to invent and add on to this field called quantum electrodynamics, which we just found out was the one thing where relativity and quantum mechanics sort of agree. But this Lamb shift was also more important than that, because not only did it start to kind of build out that world, it actually allowed things like the theoretical prediction for Hawking radiation in black holes to kind of come about. So, he laid the groundwork for a lot of future understanding, and especially in that quantum electrodynamic space. And like I said, the one thing I have problems with in the quantum mechanical space is this statistical and apparently random nature of it. That to me doesn't sit well. I think there's more underneath it. Einstein once said that it's giving us a fuzzy view of something more that lies underneath. And I agree with Einstein. I think quantum mechanics gives you a great sort of description of things we don't completely understand, but it tends to get far more complicated than I think it needs to be. So there's still work to be done in this field and others to kind of go back and say, are we really is it really this complicated, or are we just making it too hard? But this observation that Lamb did surprised everybody. And it said, well, here's this shift we didn't expect, right? Here's something we thought we knew it all. We celebrated, we threw parties, we popped champagne corks, and all of a sudden along comes Lamb and goes, wait a minute. There's more to this story. So that was what he won the prize for, was this measurement that came about and said, more to be seen here. Now let's go talk about the other half. Okay. Polykarp Kusch, whose name I am absolutely mispronouncing, and I apologize for that. He came along and did another series of measurements. So this was another time where things got a little funky in a measurement lab. And I've been in labs where you come up with a measurement and you're like, hey, that doesn't fit theory. And everybody in the lab runs around trying to figure out what's wrong with the equipment. And that's the appropriate response, because sometimes there is something wrong with the equipment. And it takes guts to look at it and go, okay, the equipment's right, that measurement's right, the theory's wrong. And I've actually published papers like that. And let's just say people aren't necessarily terribly happy about it when you do that sort of stuff. They all tend to run around and say, you must have made a mistake. And then they duplicate the measurements and go, well, darn. So it does take guts, and you will catch a lot of garbage for doing measurements that don't fit with theory. People ain't happy about it. But what happens is electrons in particular, and atoms in a more general sense, actually behave as though they have some form of rotation. So it's kind of like they're rotating on their axis like the Earth does. And charged particles generate, when charged particles do that sort of thing next to each other, they generate magnetic fields. And they also have what is known as a magnetic moment, which is a way scientists have of trying to figure out how much they interact with a magnetic field, or what kind of magnetic field you have to apply to them to get them to do a certain thing. But that's all well and good. And along came Dirac, who came up with a theory for all this. And he used quantum mechanics and the theory of relativity to formulate this new theory for interaction of all that stuff. And he came up with some theory of charged particles and electromagnetic fields. Really cool stuff, but there's a long way to go. Now, along comes this measurement, and oops again, right? So the first half of this prize got an oops, Dirac, you're not quite always right. The second part of this prize goes, oops, Dirac, you're not always quite right. And what Kusch discovered was that, and he did this in 1947, was that the electron's magnetic moment is actually greater than that which was predicted by Dirac. Yeah. So it's another way of just saying, hey, look, scientists, every time you think you've got a theory that describes everything, you better watch out because along comes somebody in a lab and says you're not exactly right. And that's really kind of the cool part about science. There's always new stuff to learn. We don't always know what application that stuff is going to have. We don't really understand maybe exactly where that's going to go, but we do want to keep digging deeper because remember, one of the earlier prizes we were talking about the electron, and that led to electronics. We were talking about the photoelectric effect that led to everything from the solar cells to grocery store scanners. Um, all kinds of different prizes that were basic science that at the time nobody understood where they were going to go went on to do great things. This particular set of prizes with quantum electrodynamics and quantum mechanics and all these things are going to lead to a quantum computing revolution, which is going to completely change the face of computing as we know it, and probably in the next 10 years. So you may not see necessarily applications of this stuff today, but there are some coming down the pipeline that you've probably heard about and may not realize they're associated with this. Quantum computing is a little different, but it has to stand on the shoulders of a whole bunch of stuff, and this is sort of one of those that are in that space that led to something that led to something that got you to that quantum computing side. Now we're going to dig into the 1956 prize soon, so don't forget to click like and subscribe. That does help us out with the algorithms. And we'll see you on the next video and try to have a good day. We're less than a week away from the Nobel Prizes for 2024 being announced, and I'll probably do a live stream the day the physics one is announced, which is actually just 4 or 5 days from now. So everybody, we'll see you again soon.